We're very happy to kick off the program with lecture by Alex Fink from Queen Mary University of London. And we're going to hear about Speyer's F-vector conjecture and proof.
All right. Thank you, and thanks everyone for coming. And apologies for those who are at IIS or Rutgers who have heard versions of this talk before, but maybe if you hear a talk for the second time, you'll understand it. We'll see. Okay. So, this is a story about matroids, despite that I didn't wedge the word matroid into the title, it certainly belongs. So I should start by giving a definition of which, I mean, if you've seen matroids, you may not have seen this definition. So this will look like the basis definition at first, the one you find in the text. So I want to have a set system, a set of subsets of some ground set, and for me that will just be, I will use 1 through n. So if I have a system of sets like this, it could be a set of bases of a matrix. And if you've seen this before, I go on to write an exchange condition, modeling the Schneider's exchange condition. You have two bases, you can swap something between them. I'm going to say it a bit more polyhedrally. So, okay, if you like the old definition, maybe there should be a theorem, and it should be like in 1970 or Delphi-Goreski, Harrison, Serganov in 1989, something like this. But you can characterize the same exchange property through a polytope. That's what I want to do. Okay, so what do you do? I'm going to take my sets. I can encode them as 0, 1 vectors. So I'll write E sub B. This is the sum of the standard basis vectors indexed by B. So it's the 0, 1 indicator vector of B. I meant to say convex hull. Okay, so this gives me a nice polytope in an n-dimensional real space. And what I want is that this thing has all of its edges in directions that correspond to your usual matrix. So, what do you do when you do an exchange? You add an element to your basis and you subtract an element. So these edges, so you can move between bases by adding an element and subtracting an element, which is matroid exchange. It's just, instead of having explicit quantifiers in which exchanges you can do, I have this more convex geometric condition on which exchanges you can do, turns out to be one. So, we should do some examples. Let's do, well, I can do the uniform matroid of some rank R on N. This has bases, all subsets of N or R. That's a matroid. I will draw the polytope. I'll give the name, the polytope of this thing has a name called a hyperspace. So if I want to draw U24, or the polytope of delta T4, okay, I have all subsets of 1 through 4 with 2 elements. I encode the 0, 1 vectors. They are 0, 1 vectors that sum to 2, so they lie in a hyperplane in R4, so it's a 3-dimensional. And I can attempt to draw a 3-dimensional, even if not. And this is general. There's always at least one linear constraint because all the bases are the same size, so that they play side. Okay, so I have these 6 sets, and it turns out, oops, let's put that in front. Turns out these 6 sets make an octahedron, something like this, where 1, 2 means E12, 1, 1, 0, 0, and I get this nice octahedron like this. And you can see all of these edges all of the edges are between sets that differ by a single exchange, right? 1, 2, and 3, 4 don't have an edge between them that go through the middle. And the fact that there's no edge there, you know, is the kind of thing that is asked for in this property. All the edges are exchanges, this is good. Right? The kind of thing that is bad is if I have like 1, 2, 1, 3, 1, 4, 3, 4 is not a set of bases on a matroid. Because you can tell this in this polyhedral model while I'm using a subset of these vectors. But I pulled off these two so that I would expose this long edge in the middle, which I said I didn't want. That edge is not a single exchange. So that's bad. And you can check this corresponds to a failure, like I can't take this basis and swap in 2 from that basis. And that's a failure that you show. Okay. So matroids, you can think of them as a kind of, maybe I will say one more example, which is representable matroids. These will be important for me. You can think of them as taking a big matrix and looking at which bases vanish or don't vanish, or you can look at them more geometrically. So if I want to say, you know, maybe I have a matrix, well, okay. I'll do the geometric thing first. Let's say I have a subspace of the vector space KVN, linear subspace for KVN. Okay. I'm going to do this in the hyperplane arrangement convention. Yes, right? So now inside L, here I have a bunch of coordinates. I'll say KVN X, so I have coordinates X1 through Xn. And now I can restrict those coordinate functions to L, right? I can look at like the coordinate functions xi restricted to L. That's a linear function on L. And okay, basis, right? I'm supposed to be using some linear algebra. Let's look at when these are a basis of linear functions on L. And if I say that those things are the bases, then I do that. Right, and this is the matrix associated with L. Index sets of bases among these functions. Okay, the fact that I work in the dual might be, you know, might be a little off-putting if you haven't seen this before, but you can dualize everything and look at spans of vector configuration, but this way is nice because it's the way it corresponds to hyperplane arrangements. You've got your linear space L, and it's sitting in a high dimension space. And well, okay, I care about these x's. Maybe I'll just draw when each coordinate is 0. So maybe the thing is supposed to be sitting in K5. And so there's some hyperplane where it's 1 equals 0, some other hyperplane where x 2 equals 0. You know, some other hyperplane where x 3 equals 0, and so on. Maybe I'm drawing projectively because I don't want this thing. You know, maybe I want to be able to draw something like that. That's okay. And well, if I choose a set, say, x1, x2, x3, these functions, all of them vanish here, right? So that's not going to be a basis of linear functions. You have some linear functions that don't vanish there. So if you've seen the matrix of a hyperplane arrangement, this is the same. Any of these ways of getting a matroid from linear algebra is called a representable matroid. You could just write down a matrix for L and then look at determinants of the matrix, maximal minors, which one vanish, which ones don't. If you've seen that, it's the same thing. So these are representable matroids. And I guess there's kind of a bunch of modern developments in matroid theory, which all have the flavor of trying to use algebraic geometry that you build from this L to say something about the matroid. And then, well, what if your matroid isn't representable? Many matroids are not representable. And then, you know, the fun is figuring out what kind of surrogate you can provide for the algebraic geometry in the case that the matrix is not representative. So I will, talk about this proof. It will have to be by necessity fairly an outline, but I'll try to give a bit of the flavor of some geometry and then some other surrogate. So, the word tropical is in the title as published, but okay, I mean the word tropical. Okay, what's the word tropical? What is this Speyer's tropical effect? So, David Speyer was looking in his PhD thesis 2005 at tropical geometry, which was, I don't know if it was exactly new then, but it was at least new in name then and kind of taking off the field. So tropicalization, I will not say a huge amount about tropicalization, but it's a way of turning algebraic varieties into polyhedral. Or maybe I can briefly say one way. If I have maybe a variety which sits in that line space, for instance, that's where we receive. That's where we receive. I have a complex variety, just to make things easy. I can tropicalize it. I can turn this variety into something polyhedral. And just if you was to say this, it's not so important what I write here, but just to show that it's a fairly concrete thing, what I do is I take like coordinate-wise log of, well, log absolute value, since I want to end up with a real number. Coordinate-wise log of the points in X. Okay, draw X on log paper, as it were. And then the base of the log. So I take my loggy thing and kind of zoom out to infinity. I just get some cones. Okay, so that's the tropicalization. It doesn't matter too much exactly what this process is. I'm not going to return to this in the top, but there's some way to take a variety and turn it into cones. And so, well, for instance, if I start with, say, L is a plane in C4, two-dimensional thing in C4, matching this example. Let's say it's generic, so that it doesn't have any unexpected zeros in the matrix or minors vanishing or anything like this. Well, then you can tropicalize it. And you get a thing that looks like this. You get something with 4 rays. Oh, this stuff is sweet. I'll have to live with it. You get some union of 4 rays that looks like this. And so, well, Speyer was trying to figure out what tropicalizations of linear spaces are and had a theorem, 2-part theorem. The first part was that if you do this, the tropicalization is determined by the matrix. Maybe you can see these logs are kind of recording how quickly coordinates approach 0 and how quickly coordinates approach 0 is this plane the matrix. So it's not so surprising this is the matrix, but indeed it is. So I'll have 2 parts. The tropicalization is determined by the matrix. And how does it look? Well, this is dual to a subcomplex of this. If I draw in dual space, I draw this octahedron here. What I have is actually, I have selected just the normal going through certain faces. Which faces? They're exactly the faces which don't have a coordinate vanishing. For instance, this front face, 1, 2, 1, 2, 2, 3, X4 vanishes on that. That's a bad face. 1, 2, 1, 3, 1, 4, no coordinate vanishes on that. That's a good face. I stuck a yellow. So it's determined by measured in that. Okay, there's another variation of tropicalization I won't tell you, where you have a valued field instead of C, you have a field with some valuation, and you can do a similar process, and you get something else. If you start with this, okay, instead of getting 4 rays at the origin, you will get a picture that looks a bit different. Okay, it kind of, collapses to this, but I've taken this vertex and distracted it into two different vertices of degree 3 like that. And so, okay, if this is determinant of the matroid, is this determinant of the matroid? Well, it turns out to be true that if you collapse this picture, you get back to here. But you can say what the structure of this is in a much richer way. But if I do this valuated localization, this is determined by a way to subdivide this polytope, we're going to cut off this polytope into more matroids. A matroid subdivision. Okay. Other matroid. And this edge criterion for what matroids are is nice because it means dissect it into matroid polytopes. It just means dissect it without making any new edges. So the kind of dissection you can do to this is I could cut it along this square in the middle, and if I cut the octahedron along this square, no new edges, I just get this top square pyramid and the bottom square pyramid. Those are both matroids. And indeed, in the same way as this picture was dual to just the octahedron, this picture is dual to the thumb. I have this thing for the top square pyramid. I have this thing for the bottom square pyramid. And they're joined because I pull it apart there, but I cut there. Okay, so I will not ask me if you want detail on tropical things, but on account of this, David was motivated to study matroid subdivisions. And the titular conjecture is indeed about matroid subdivisions, and is maybe the first question a combinatorialist would ask about such subdivisions, namely, how many pieces could there be? Extremal combinatorial question. How many pieces can I cut a matroid polytope into without making the edges? Maybe you can see I can't go finer than this in this case. I can't cut the square pyramid any finer without making a new edge. So this is kind of as far as you can go here. So David conjectured this in 2005, and then he proved it, I think, in 2009, when your matroid is representable and the field is the complex numbers. And Andy and I proved it in general. What the extremal numbers are here. And I've made enough note space to state the statement there. So this is the kind of thing which, because you can write down a random linear space, a random matrix easily enough in this valued field setting, you can get your computer to make lots of examples of these and then count. And it's fairly easy to come up with lots of data. And well, it's actually, if you pick randomly, it's quite easy to come up with something which has what looks like the maximal combinatoric. So this conjecture is something you're led fairly quickly to, and I'll copy down the trinomial coefficient here. Okay, the number. I'll look at interior faces, just because they're the ones which are like bounded when you dualize like this, and it's easy to adjust the count to throw it together. Interior, codimension I, faces in a matroid subdivision of the uniform matroid, the hypersphex, if you will, uniform matroid, as a bound is bounded above by a trinomial coefficient n minus I minus 2 factorial, I factorial, r minus I minus 1, and this is. So I guess you can check, right? Okay, what did I do here? 2, n is 4, r is 2. If I is 0, you get 2, choose 1 is 2. There's 2 codimension 0 things. If I is 1, you get 1, choose 1, and there is 1 codimension 1 thing here. So these trinomial coefficients seem to be governing the maximal combinatorics. So, questions so far?
So when you say matroid plus polytope, you're talking about the basis polytope.
The matrix, yeah, these are the basis points. People look at other things like independent set polytope or things like that and do basis polytope. That's right. Yes.
Can I talk about equality, please?
Can I talk about the equality case?
Yeah, when?
I can, yes, okay, so it turns out it's equal when all the matroids are series parallel in the sum. All the pieces are series parallel. Complex. And there's a nice way to exhibit these, like if you know lattice path matroids, you can exhibit one where you use the series parallel lattice path matroids. Yes.
Is there like more combinatorial justification for where this kind of coefficients are?
I would love that. I will give you an algebra geometric character. Okay, fine. I'll show you this construction. This is combinatorial, right? Okay. So this is the lattice path. So how the lattice path matroids work? You know, I have some r by n minus r box, and maybe I pick a skew shape within it. And once I pick the shape, okay, let me pick a snaky skew shape because these are the ones I'm going to want. And once I pick this, once I pick the skew shape, I say the bases of the lattice path matroids are all paths. Well, they come from paths that stay within the skew shape. And what is the basis? Well, I went up on step 1, 2, 3, 4, 5, 6, 7, 8, 9. I went up on step 1, 4, 7, 9. So 1, 4, 7, 9 will be one of my bases. That's the lattice path. Okay. Turns out all of these lattice path matroids for snakes or ribbons, these shapes without a 2x2 box in them, they give you a maximal subdivision to these snake. So there's an example of this type by these snake lattice path matroids. And okay, the top dimensional pieces look like this, but if you go down in dimension, the dimension of your matroid polytope, the codimension of your matroid polytope is the number of connected components. So if you go down in dimension, you start making it disconnected, and it's no longer one snake like that, it's a connection. It's a bunch of snakes live together in corners. Okay, so what's the trinomial coefficient counting here? Well, I need to make my snake or, string of snakes. I can go up or right or, diagonally across a corner in each case, and that's this binomial coefficient. So, in this subdivision, I know how to say what the combinatorics is. In general, I only know algebraic geometry. But at least there's some nice combinatorics here.
But the fact that this is a different algorithm, but presumably that means somewhere in the proof there's something that indicates why this particular matroid or this particular flavor of matroid is maximal in that one.
Yes. Well, okay. I'll tell you the technique. The kind of all of this work has used the same technique, and it's some kind of like measure theory, right? The technique is if I want to cut this up into pieces, and each piece has a size that's bounded from below in some sense, then that also gives you an upper bound on the number of pieces. So that's what we want to do. So series parallel matroids will have a minimal size. Okay, so, well, all right, this is where the talk is going. So let's kind of make this notion of size or measure formal. This is what's called a matroid valuation in the biz. I'm going to use co-valuations just so I don't have to think about signs because the signs are messy. Okay. So a function from matroids, from the set of matroids, or whatever, to an abelian group G. Is a co-valuation if it is additive in the subdivisions. And the way I mean additive is kind of not the on internal face, on interior face. The way I mean additive is not the inclusion exclusion way you might think, right? If I was doing inclusion exclusion, I would maybe say this octahedron is the square pyramid on top plus the square pyramid on the bottom, and I double counted the square, but I want not to have sides. So I'm like thinking if you like, the interior of this really is just partitioned into the interiors of those three things. So I'm like the relations among interiors of polytopes. And if I use these relations among interior polytopes, you can always have all pluses, and that's good if I'm trying to do this bound by the size of the pieces. Okay. So the strategy then is to give you a co-valuation, let's say like natural value, so the pieces have size at least 1, that gives you this on the whole hyperspace. So that's the strategy. So, well, there is such a thing. This is what the data did. So there exists not like this, a co-valuation, beta value in polynomials in one variable. Why polynomials? Because I want to track all the dimensions at once. So I'll use a coefficient for each dimension. I'll index it by codimension, and I'll add one. That turned out to be well. It's nice. Okay, so I want it to be right. So that what do I want? I want beta of m is going to be some all right, let's say it has this, sorry, not beta, I'm getting ahead of myself. Beta is predicate beta, and that's in this story, but this thing is called G. Sorry, G is some coefficient, let's call it A of and here the coefficient I want is the codimension of m in Rn. It is the same as the number of components of them. So let's call this number C. So I want AC times to the C plus higher order term, where AC is positive. So that actually AC, it has a contribution that's positive in the dimension it should. And well, this is not so bad to show it's positive here. Turns out the tricky part is to show that there aren't negatives later on. And so David conjectured, and the thing we showed is that actually it's positive. And then right, every matroid has a positive side in its dimension. There will be some correction terms, but they're also positive, so it will break the attempt to derive it out. Okay. So David defined, yes.
Can you say another sentence about what you mean by additive and subdivisions on interior basis?
Right, I wrote this equation, but this was meant to be the kind of equation that the function has to satisfy. So anytime I have a polytope, and I can subdivide it into more polytopes, then I demand that the function on the whole is the sum of the function on all of these interior faces of the pieces, not just the top, the maximal ones, but also anything else inside shared by it. It's not in the boundary of the big thing.
Okay, thanks.
Yes, okay. So defining this thing is where we start getting algebraic, but we can say a few combinatorial things about it, a few properties of it. So why did I accidentally write beta? Well, because Trapose beta invariant is the linear term. There's no constant term because I said the number and the number of components is at least one. So I'm going indexing by number of components, so t to the 1 is the lowest. Yep. Okay. So some facts. Okay. There's no constant term. The linear term is Trapose beta invariant, which I guess, is the classical faction of the invariant fit right in this story. Okay, so this is a matroid function, which is a non-negative integer. It's 0 if the matrix is disconnected. Good. That means it should be in lower codimension. We shouldn't see something here. It's 1 if the matroid is series parallel. That's this fact. Otherwise, it's strictly greater than 1. So that's the kind of thing we need. And now we need that kind of thing for higher dimensions. And, well, I mean, maybe it's worth saying a few facts that G of, if you like matroids, I can say that G of a direct sum is G of the product. And G is unchanged by series and parallel extension. And I say these facts because well, I guess I need a base case. If you know these facts and this co-valuative property, that's enough to force there to be at most one invariant G that has these properties. You can play with fitting your matroid into subdivisions and subdividing your matroid, and you have enough relations to show that there's at most one invariant that's going to have these properties that will do this. But showing it's actually well-defined, well, that's a bit tricky. So the definition, a few different forms of this definition have been given, but they're all algebra geometric. And so it's time for a bit of that. Okay. Let's define this G. Okay. So how is this going to go? I'm going to get it from some sheaf cohomology of some vector bundles. Okay, holomorphic Euler characters. So this is, we can do this right. Okay, let's work with the complex numbers because David and us both needed some complex geometry vanishes. So I want to define it for a representable matrix first, one that has a subspace L, and then I'll say it. Okay, so if I have a subspace L from C to the N, linear subspace, I want to make some vector bundles. Here is how. Okay, so I have the C star to the N, the algebraic torus acting on this just by coordinate multiplication, and that acts on my L as well, right? I can translate my L around into this action. And so using that, I can form some line bundles over, I'll call it T. You can make a line bundle over T that is, you're going to have T equivariant bundle. That just means they have a T action. Well, one of them I can put L over the identity and then just move T around. I get a different subspace for every element of the torus that assembled into a vector bundle. I'll call that one SL. S for subbundle. Right? So I want this to be, if you look at the identity, you get L, and then you move it around with it. In a similar way, complementary way, instead of starting with L, I can look at the quotient space. The mod L, that's another vector space. And I can move that, I can translate L around that, gives me different vector spaces like this as I act by the torus, and I can patch those into a vector bundle too. So I get these two vector bundles on the torus. And then, well, it turns out that there's a nice compactification of the torus you can put here. Let's do like this. I'll just write X10, where X10 is the toric variety of the permutation. This is where a lot of this modern matrix theory, algebra, and geometry have. Just some compactification of T, which is fine enough that when I try to like take the limits of these vector spaces as they go on to the, like as coordinates become 0, I can do it. This is just something, some base resolved enough that I can actually put limits and extend these two bundles. So, okay, so I get these two bundles with fibers that are translates of L and fibers that are translates of the quotient. And then, okay, if M is representable, okay, so I'll give if M is L, then G of M is going to be okay. So it's some sum of okay, -1 to the number of components of M, and the sign generating function indexed by T minus 1. Okay, so we're off by 1. And now I take the sheaf Euler characteristic of a wedge power of this thing tensor with a wedge power of the dual of the other. Okay. Why do I do that? Because the computer said so, right? David and I did a bunch of Mathematica experiments in 2010 or something, you know. We had reasons to think these were good ingredients to use, but in what combination? Well, run a bunch of examples, do some linear algebra, this combination. Okay. That's that gives you the properties you want, being these. That's going to be the kind of measure. Okay. And okay, what if M isn't M of L? Well, okay, it turns out that if I've said it's a co-valuation, this is actually all you need to do because you can always relate any matroid to representable matroids using these subdivisions. So I could get away with saying that, but instead I will say something probably just as unsatisfying if you haven't heard this stuff before. But if M is not M of L, it's general. Well, we don't have L, so I can't build these things, but I can build some kind of surrogate. This is, okay, there are classes in P equivariant K theory. Of this. In other words, splines. That is, okay, talk to us later about why this is spline. But these are just some particular splines. These are some nice splines defined in the edge graph of the permutahedron. So they're exactly, this is one of these spline rings, which you will be hearing about in an hour, I believe. So in fact, you can actually model all of these things by splines, and then you have splines for matroids, even if you don't literally have these vector bundles for matroids. And then there's a way to do this computation in that setting. This way of working with the matroid. Okay. So these are very concrete splines, like you record the lexicographic first basis for a given order of the ground set at every vertex. This is supremely combinatorial stuff, but it's, you know, it's doing what it's doing because it's trying to emulate this algebraic geometry. Okay. So I will try this. I will try to tell you the big beats in the proof in my remaining 50 minutes. If people are happy, or at least not protesting. Okay. So there is one thing that there's a piece of work that I started with David Speyer and Chris Shaw at the field is a theme semester in 2016, and we finally got to the archive in 2024. So, you know, that is the speed at which people can manage to write things up sometimes. But the first step, okay, I'm going to prove. The first step is from there.
Only one question.
Yeah.
This, L was a one-dimensional space? or what?
L can be any dimension.
Oh, I know. But then why line bundle?
Oh, because I said, I hope I
vector.
said
Okay,
vector.
good.
Did I say vector or did I say line? Vector bonds.
Vector.
We can-
Vector bonds, of
At-
course.
At the end, we
At
can
the
check
end,
the
we can say,
recording and
Only-
find out for
only the
sure just
YouTube
how
audience can tell.
wrong.
Okay, vector bundles, of course. Yes, thank you.
And this is related to, so that seems to be that you're using like the tangent sheet, the Grassmannia. And
Yeah, that is, I mean, right.
Mhm.
There, yeah, I mean, you can, like, you want to, one way to interpret this is like the wonderful variety is the top, like a section of the top wedge power of that tangent bundle. And so you can get this formula from doing, turn one of these into the wonderful variety, and then you're looking at the other one, like the tangent. You'll get my end. I can't explain why it should be that in those terms, but you can look at it in those terms. Yeah. Yes. Okay. So the first thing I want to say is that you can show, okay, so I said the bottom coefficient that doesn't vanish is the Crane-Coste invariant. And we want to understand the coefficient at the other end. Turns out that the degree of this thing is at most the rank R. So let's give that a name. Okay, using the guided Greek letters, the omega is the last Greek letter. So let's say omega is the last coefficient, the coefficient of R. And that's rank R. So the proposition is that if given an n, you can show that if this thing is positive for all minors n of m, that's actually enough to show that all coefficients of the big thing are non-negative. There's like a way kind of what do you call it, convolution style formula that will turn the coefficients of this into betas and omegas. It's okay, the betas we know are positive, so the omegas are positive. Okay, so this is the guy we want. We want to show that this top coefficient. Okay, now we do an interesting thing. Okay, there is one linear space here. We're working with the function of one matrix, but we actually want to generalize to two. Right, I could imagine putting some, this is some L1 and this is some L2, or in general, right? I could imagine looking at M1, I use this spline here, and then I use this spline here, and I could actually take the ones that come from different matroids, and there is some way to, some like divided symmetrization on splines that this is. And so, but the point is I can put a different matroid in here and in here. And the reason it's useful to do that is because now if one of them is a line, if one of them is rank 1, if let's say M2 is uniform of rank 1, then we get to a situation of, it was worked out by Federico Ardilla and Adam Bicker in 2009. They have this paper on the closure of a linear space in the product of lines, a variety that's now called the matroid Schubert variety by the kind of people who are at IS right now. And these two did a whole bunch of work on the Matroid-Schubert variety, and in particular, like we do this generalization kind of for a genuine mathematical reduction reason and for inspiration. Right? They have a bunch of results about this Matroid-Schubert variety which show, oh, it's related to a certain nice simplicial complex, which is the external activity complex of the Matroid, which I'm now calling M1. And so a lot of geometry about this thing is encoded, encoded in a simplicial complex. Kind of the external activity complex of M1. And so we need both to kind of follow this by analogy. We're going to be doing some kind of external activity complex in two matroids, but we also do need to reduce to their case with some sort of like commutative algebra. Okay. So once we make this generalization, okay, now we I guess kind of the strategy is I want to do something algebra geometric, and then I want to mimic it with combinatorial tools, find a way to do the combinatorics that bypasses the algebraic geometry in the case that it's not there. So I'll say, for the people in the room who like this kind of thing, okay, the representable case. What do you mean? So this is M1 is going to have M1 and 2 is going to have M2. Now I've got both of them, and I want to look at this thing, and it's okay, just the top, it's just the top coefficient, so it's the rth wedge power of this thing, and the rth wedge power of this thing. And okay, where R is the rank of M1. And since this is a rank R vector bundle, this thing is one-dimensional, that's a line bundle, and so that I can dualize to be another one of these cubes. Apologies, this belongs over there, but I've just written it here, so I can here. I'm just going to turn this into n minus r of the dual object, and r of this. Okay, so we have this holomorphic Euler characteristic. Kind of the goal is to turn it into some kind of simplicial complex. In large strokes, 2 steps. First of all, this is a vector bundle. We'd like to get away from the vector bundle setting and then just work with a single algebraic variety. And then the second step is some kind of initial degeneration to turn it into a simplicial complex. The second is maybe a familiar step if you've done some combinatorial commutative algebra. The first is a less familiar step. Okay, I guess this is what this is a technique which we learned as we were writing this up. What you want to do is take basically all of these. I have all of these different vector spaces, wedge of L, this wedge power times this wedge power. Well, I want to go with yes. Okay, I want to go with yes. I want to go with the dual of this because I want to. Let's see what we have. Okay. I want to go with my S vector. Okay, so I can take the direct sum of my 2 vector buckets. That's fine. These are right. L the subspace of C to the n. L2 is a subspace of C to the n. So this thing is a subspace of C to the 2n. I can write, well, C to the 2n, just a trivial bundle of C to the 2n fibers. Every linear space in here lives in C to the 2n. And I can just take their union. So what I'll do is I will take just the union of all fibers. And I'm going to say this is like project away, project into the C to the 2n, and I get a variety that just is the union of all the fibers in here. We call it y axis, the phasor of the L2, just the union of fibers. And this is a very concrete thing. It is actually just like I take my L1 and L2 and I hit them by a torus. Just T times U, T times B, where T is in the torus, U is in my first case. So this set of all things that are obtained that way. For some T, I just added all these things together in one variety. That's what's called Kemp collapsing. Kemp was using this in 1975, I think, for like weak theoretic PWB type arguments, but for all they thought. But here it works perfectly nicely too, and it gives us a single affine variety, which encodes our whole vector bundle. This is a term of the Kazul resolution for this. And the magic of Kemp collapsing is that under nice conditions, which we have, magically you get a free resolution of this, which has the same information in it. So now this thing, let's call this the green star. So we have a Kazul complex over here. And so the resolution of this has a resolution, a free resolution, that knows green star. This is like Diamond's. Okay. So I kept the invariant I want, and I moved it to here. Now I want to get a simplicial complex. So how do you get a simplicial complex? You do an initial degeneration. And further magic happens. Every initial ideal of this guy is a square Freeman field. It's the same shape of free resolution. Normally, you expect free resolutions to jump when you do a generation. They don't in this. The same shape of free resolution. So it also knows this green band, right? It knows this green stuff. And then, okay, how does it know the green stuff? Well, it will be like Hochster's formula. It will be the sum of some Tor groups of some things. Okay. Conclusion. Omega M is going to be the sum over certain bases, F something, for something of F of the resulting simplicial complex. So I didn't name the simplicial. Of the simplicial complex, you get this is the initial. The complex whose spaces are all the monomials now. So due to two pieces of magic that say we had this like term in a Kazul complex, and it survived when we collapsed the bundle, and it survived when we degenerated the collapsing into a combinatorial object, due to both of those surprises, this is like combinatorial formula. This is the radius reduction. Both of those surprises, the function we want to be rid of a simplicial complex. Okay. Now, the combinatorial part, this was the representable case. The non-representable case is first to interpret this. First, to interpret this as something combinatorial, well, I've already hinted this. This thing, I want to put matroids in a bit of linear space. This is going to be an external activity complex. For two matroids, we have some notion of external activity complex that's constructed using the so-called diagonal Dilworth truncation. Ask me if you want to know about it. And then we have to. And then we have to, well, find some reason, now that we've torn the geometry away, find some reason that this thing should still be encoded in this complex in the same way. And this is by, well, some sort of like tropical intersection theory of chain classes of our swap. And, you know, either ask me or watch the 2-hour IIS version of this lecture if you want to see a little bit of this, but I think that's a good one. Thank you.
Please, are there any comments or questions? If they go ask. Yes.
So at the start, you said that you were checking something for the computer.
Yes.
Were you checking the ones that were like visible in 3D, or were you checking like the combinatorial factors?
We're checking the combinatorial. It's okay. So we had these combinatorial properties, you know, multiplicative indirect sum, unchanged by series parallel extension, right? You could use this to produce a bunch of examples of matroids and the value this thing should take. Then we had a bunch of like algebrogeometric ingredients. Okay, we thought like things like this were relevant. Actually, we're thinking like Schubert calculus on the Grassmannian at the time, but these can be re-expressed in Schubert calculus on the Grassmannian. And so we took like all the Schubert calculus on the Grassmannian. We wrote like a big, you know, matrix. On the one hand, you know, the polynomials we want. On the other hand, like all the Schubert invariants of the matroids, you know, do a big linear algebra problem, solve for what we should be doing, and it spits out some coefficients, and then stare at the coefficients and try to extract the pattern in them, and it's this thing. Yes.
So what do you recommend for mainstream matroid theorists to get into this?
Yes, there is. Okay, so in terms of like readings or
just, you
Or
know,
just,
start
like,
working in this?
start
There's
working in
so
this.
much overlap.
yeah, there's a lot. I mean, yeah, it's very active. There is. In particular, this work did not use any matroid Hodge theory, and that is very. And people are using matroid Hodge theory to knock things down all over the time. And maybe matroid Hodge theory is reaching the end of like the easy exploitations of it. But there's, I mean, there are a lot of combinatorial ways into this. Eric Katz has a nice paper, matroid theory for algebraic geometry, which is the answer not to your question, but to the opposite question. But like more recently, Federico Ardilla has like a series of papers, The Geometry of Geometries, which are kind of more like this, algebraic geometry for matroid theorists. And it's a nice survey, I think, of the kind of tools that come up here, like Bergman plans and hydrolysis flats. And, I mean, partly, you know, what are the questions that I don't know, structural matroid theory wants to investigate? Which of them might be good to hit with hammers like this? That's a side of the question, which I think only by talking to each other.
I brought this to I can already like take this as a whole valuation language.
Yes.
I guess like up to they have nice properties.
If you know about valuations, co-valuations are just sign twists. I multiply by -1. Yes.
Can you explain a little bit more about what goes into 3D? Because if I do an initial degeneration, I would almost never expect it to be miraculous.
Yes, this is. Okay, so this is like, the technique here is, or the theorem here is that these things are Cartwright, Schoenfeld, Starlight. They are, these three have a sequence of papers about taking multi-graded generic initial. So I have polynomial ring and a set of variables. In this case, I have the polynomial ring in two n variables. And I kind of give them the Zn grading. Well, the fact, it turns out, if you pick just Zn graded generic initial ideal of this thing, you get the same as if you take Zn graded generic initial ideal of their thing. And both of them are ideal. The generators are all in the X. You don't see the Y's. And these three, you know, they're mainly looking at like the dual property of this, the Alexander dual property, whatever. But on our side, it says if you have an ideal, a monomial ideal, whose multigraded gen uses only one variable of each degree, then you have a whole bunch of like facts, like you can pull back through resolutions, you can lift the Cohen-Macaulay property, like you have very nice regular sequences. This is the commutative algebraic workhorse.
There are more comments or questions. I think I will